Okay, so we've learned a little bit about collisions and the conservation of momentum during collisions. And now I want to bring up this term that's called impulse. And what it's going to do is bring back the concept of force, because of course force is involved in collision. So during collision, objects change their momentum from by gaining or losing to other objects. It's very often useful to consider the actual change than to examine the starting and ending values. And so what we call a change in momentum that an object undergoes, this delta p, is actually given a name, and that name is the impulse. Um, okay, and impulse change in p is m delta v, the mass of an object times whatever change in velocity that the object underwent. Um, but if we remember that our acceleration is change in v over t, or change in time, then change in v is also a delta t. So we could resubstitute that back in over here. So we would have m, but instead of delta v, we can just write a delta t. And from Newton's second law, we also know what ma is. Ma is just a force. So F delta T is equal to delta P, right? And so the impulse is also a force exerted over a time interval. And sometimes in collisions, that time interval is very quick. So, and it involves two objects, one object against another object, and it involves Newton's third law. Because if a car hits a one of the let's say just backs into a pole, okay, the pole exerts a force on the car, and the car exerts a force on the pole, and they're also in contact for the same amount of time, so that their impulse change is equal, but of course opposite, because one is from a force in one direction, and the other's of a force in the opposite direction. So when two things collide, they hit each other, and that brings into mind Newton's third law. And they hit each other with the same force and over the same time. So when a bat hits a ball, the bat is touching the ball for the exact amount of time as the ball is touching the bat. This implies that the impulse on the bat and the ball are the same in magnitude, but opposite in direction. It also tells on the design of many things to try to keep us safe when we undergo a collision, like in a car accident or with a helmet in football and things like that. They're designed to give way for various, for longer amounts of time, because if a change in momentum occurs, you're going to go from some speed, say, to stop, a change in velocity, and you have a mass involved. So there's that change in momentum. But now we know the change in momentum is also the force times the time, okay? And so the force times the time, well, you could have a smaller force if you, per unit of time, if you exert it over a longer period of time. So if you increase the amount of time, then the force per unit time is smaller, and to produce that same impulse. So that's why we have padded dashboards, and we have airbags. That is increasing the amount of time that over the collision as we stop. Instead of just hitting a brick wall like that, we extend that amount of collision. The same thing happens with a car. It's colliding. It's crumbling up in front in a front-end collision. The engine's going down, and it's extending the amount of time that force occurs for that impulse and change in momentum. Okay, here's an example involving impulse. A 0.2 kilogram puck is shot towards the goalie at 20 meters per second, and the goalie feels a force of 60 newtons as she catches the puck in her glove. How long does it take to stop the puck with her glove? So her glove catches the puck when they collide. And as they collide, the glove exerts a force on the puck, and the puck exerts a force on the glove. And we know what this force is. It's 60 newtons, one in one direction, one in the other. And we know our impulse change in momentum is force times delta t. And we're given that fact. And we also know that delta p is m delta v. Okay, so the mass of the puck is 0.2 kilograms, and it's going to a stop, so it's 20 meters per second is our change in delta v as we go to 0 for our VF. And then F is 60 newtons, and we're wondering how long it's going to take. So we can see that delta T is 4 kilograms times meters per second over 60 newtons. So delta T equals 0.067 seconds. And so a short amount of time to stop that puck. Okay? Now, the units on this, kilograms times meters per second over newtons, we could look at that a little more closely. Kilograms times meters per second over newtons, which is kilograms times meters per second squared. So those cancel. And meters per second divided by meters per second squared is the same as meters per second times second squared over meters. So that gives you seconds. So that works out. That's good. Now, another way we analyze impulse is sometimes we look at what are called impulse graphs. And this is just plotting up the force over the amount of time. And so we'll do this when we do in lab. And some of you have already done it, and you've gotten the average force by looking at your data and your graphs without realizing that force versus time is an impulse graph. So if we plot up, for example, something like this, force exerted over time, well, we can see that the area under this curve, okay, the area under the curve, or the area under the graph between the time axis and the lines is equal to force times time, or it's equal to our impulse. Our delta P is the area, okay? So delta P equals F delta T equals the area. But of course the force isn't constant, is it? And so it's actually average force. So to write average force, we put a little bar over it like that. And the best way to find this average force is to get delta P. Now you might get the delta P sometimes. You get a delta P algebraically, like we done algebraically, or sometimes you get it by the area under the grass, and we'll do examples like that in class. Okay, and that's topic 6.5.